Welcome to this video. My name is Mark Sithian. The date today is August 24, 2024. So this video presentation analysis is going to focus on electric vehicle energy density and cost analysis. So feel free to share the data presented in this analysis regarding your research, the comparative analysis between gasoline and electric vehicle performance and cost. So we have to take the average values of electric vehicles in 2024. So the average range is 255 miles. Typical weight is 3,300 pounds. Typical cost, $56,520. And then the cost after 100,000 miles for the battery cluster is about 10 grand, usually covered by a warranty. And then our typical battery weight is 1,000 pounds of the 3,300 pound EV curb weight. And then our typical battery specifications and cost, including the lithium ion polymeric cluster having 350 volts DC and 230 amp hours. So that is as if the battery is discharging its total current capacity for 1 hour. So then we have to switch gears here to the potential energy per 1 US gallon of gasoline. So that is 126.72 joules, 126.72 megajoules of potential energy for 1 US gallon of gasoline. And the typical gasoline mile per gallon fuel economy is 22 miles per gallon on average. And then the average cost per US gallon of gasoline in the United States in 2024 is $3.45. So we have to find a potential energy differential between the range of the EV and the fuel economy of the gasoline car. And then we have 11.59 gallons of gasoline equivalent to charging an EV with respect to electrostatic battery charge. So if we isolate only the usable power or the brake power, we have the power lost to keep any dynamic power system running, the friction power. When we add these two, the brake and the friction, we get the indicated power. And then, of course, the efficiency with respect to the gasoline engine has the thermal efficiency of 30%, 70% loss to keep the engine running out of the gasoline, minus 5% loss to aerodynamic drag and tire rolling resistance. And so after the DC electricity is inverted to AC power by the AC power inverter on the electric vehicle, the electromotive efficiency of the AC electrical motor is 85% efficiency, also minusing the 5% to aerodynamic drag and tire rolling resistance. So then if we were to take the difference between the overall efficiency with respect to the electromotive powertrain only, because there's another 10% that will be lost in the electric vehicle for the conduction efficiency, because in the digital solid state electronics we don't have any wires, but we do have a crystalline structure, and the EMI inductive loss, it's about 10% more. So I'll cover, that's going to come after this calculation, but we have to take the electromotive or the motive powertrain differential of 0.8 subtracting 0.25, and then its reciprocal. So we're going to get a value greater than 1 times the potential energy with respect to the brake power at the gasoline's medium. So we'll do the EV's medium with battery power afterwards. So this then scales up to 667.478636 megajoules potential energy with respect to the usable or the brake power. And then the average fuel capacity of gasoline automobile is 15 US gallons for the tank. We take that times the chemical potential energy of 1 US gallon times the overall efficiency during the highway driving of 25%. So this then scales itself to 475.2 megajoules potential energy with respect to usable or brake power. So we have our brake that's usable, power loss to keep the motor engine running, that's the friction. We add the two together, we get the indicated or the total. That total power is the potential energy metric with respect to the battery or the gasoline that has not been consumed. So that is like the vehicle's off and you have a fully charged battery or a fully refilled fuel tank. So that's the indicated. So the last part, with respect to the potential energy, is then calculating the range calibration or the coefficient of range calibration. So in this case, it becomes 330 miles divided into 255. That becomes a coefficient, a range calibration of 1.29. And so then we're able to find the 1-to-1 ratio of the potential energy, usable potential energy curve across the EV's battery and the gasoline car's gasoline. So there is a step 1 report here excluding efficiency losses across DC to AC inverted AC motor efficiency, 15% loss, and gasoline engine, 70% loss, plus the aerodynamic drag and tire rolling resistance losses of 5% on both vehicles. The brake usable potential energy is 613.008 megajoules for the gasoline car and 667.478636 megajoules for the EV. And that is due to the higher efficiency of the EV. But the overall outcomes have to then be taken to step 2. And so this then moves into the charge maintenance, either filling the gas tank or charging the battery. So that's $3.45 times 15 gallons plus 2, 3, 4 minutes of downtime, filling your gas tank at $51.75. So the average electric vehicle charging time, as if the entire battery's been discharged. Most EV owners don't let their batteries go down that low, but if you had to charge it from a completely discharged state, it would take about, on average, 12 hours. And so that's charged from a two-phase 110 VAC 40 amp specialized circuit at 60 cycles per second. So that's at your house, not a charging station. And it could be a 220 pushing 40 or 220 pushing 20, but it doesn't really matter because we have to take the power factor at 110 volts pushing 40 amps. And if it was powering a heating element rather than charging a battery, it would be a perfect 1.0 power factor, and then the AC behaves like DC. But because you're not at a perfect 1.0 power factor, you're just right below it, 0.99 power factor. That is the 110 VAC times 40 amps, or 440 volt amps, and then multiply times 0.99, and the 440 volt amps of apparent power then becomes 4356 watts of AC true power. So it is the AC true power in watts is what you want to calculate, not the apparent power in volt amps with respect to AC electrics. So we have 4356 watts of AC true power divided into 1,000 for the kilowatts times 12 hours. So this becomes 52.3 kilowatt hours at 18 cents per kilowatt hour on average in the United States in the year 2024. So that will cost $9.40 to recharge the EV plus 12 hours of downtime, whereas it will cost $51.75 to fill up the gasoline automobile's tank and about 3 to 4 minutes of downtime. So we have the charge maintenance differential replenishing the PE, or the potential energy. So we have to take that into consideration. So next we move into the step 3, which is the total potential energy differential, 15 gallons times the chemical potential energy per gallon of gasoline. And then we have to compare this to the untapped potential of the fully charged electric vehicles battery. So that's 350 volts DC times 230 amps direct current. And so if that was all discharged at the same time, it would incur over an hour to discharge the battery, 80,500 watt hours. So we have the DC electrical power is equal to volts times amps. So this 80,500, now the volts times the amps in DC circuits becomes watts. And that is watts as in 80,500 watts for 1 full hour. That is the potentiality of that battery. Then we have to isolate or separate the watts or joules per second from the time with respect to seconds. So it splits into 80,500 joules per second times 3,600 seconds to an hour. So we get 289.8 megajoules per second if the entire battery was discharged into its full potentiality in 1 second time. So that would be like an explosion, right? So we have to go from the kinetic endpoint as if we discharge the entire battery in a second and reverse it back to the potential energy, in this case to get the potentiality. So some do wonder, how do you correlate the joules per second, which is kinetic energy, to the joules, which is potential energy? And you have to just theoretically blow the whole battery up, discharge everything in 1 second. And so we just did that on the computational level. So then when we reverse the kinetic to potential, we have a clean, accurate sequence of events in reverse to then infer the 289.8 megajoules of potential energy based on this accounting of 25 to 80, and then of course there's going to be 10 more percent subtracted on the EV for the conduction efficiency, and a lot of that's from the EMI fields that draw back voltage out of the circuits. That's why there's several non-radioactive isotopes that comprise the plasticization of the materials. So this is why some of the components on electric vehicles are super expensive, is because if you just put a bunch of electric and magnetic systems on an EV, you will then end up just discharging that battery pretty quickly from the EMI fields. So based on all of these and 3 steps, we have the total PE differential across EV to gasoline, across EV, it's going to be EV to gasoline is a 6.55 to 1. If we go EV, then it's 1 to 6.55. So that just says the EV is 6.55 times more efficient than the gasoline automobile. So this then comes to the nearing of the end of this presentation, is the cost per joule with respect to gasoline and EV battery. So that is step 4. So if we take the $3.45 per gallon versus the $10,000 every 100,000 miles with the battery, and we're assuming you didn't have a warranty, but if you did, then it's covered, right? But one way or another, the consumer is paying for it in the long run. You know, maybe you got 2 or 1 warranty replacement, but then it catches up if you take that EV into a longer life cycle. So it's 100,000 miles per battery, and that's 100 to the third power divided into 255 miles range. So that's 392 charges times a 289.8 megajoules as the divider or the dividend, and that's all over 10. That's 10,000 taken over that product dividend. So this scales to 8.8 times 10 to the negative 8 power dollars per joule for the EV, and the gasoline comes to 2.7 times 10 to the negative 8 joules per dollars per joule, I meant. So we got to go dollars per joule. So obviously it is less expensive to go with the gasoline, and so the electric vehicle is 3.25 times more expensive to maintain, charge slash potential energy slash quote unquote fuel compared to gasoline car. So we have then the final metrics and conclusion. The electric vehicle, 1.4 times more expensive to purchase compared to gasoline car. Electric vehicle, 6.55 times more overall efficiency compared to gasoline car. Electric vehicle, 1.29 times less range compared to gasoline car. Electric vehicle, 3.25 times more expensive to maintain compared to gasoline car. And then finally, the electric vehicle, 1.09 times more usable potential energy compared to gasoline car. So there's a final concluding statement here, and I'll just read this out. Materials needed to produce electric vehicles include plastics, epoxies, polymers, non-radioactive isotopes, and composite fibers, all of which are derived from crude oil, rare earth materials, synthetic materials, and factory electricity powered by the burning of crude oil. The emissions incurred during EV production are comparable to gasoline car combustion emissions. Modern cars from at least 2010 to the present, now in 2024, limited to CO2 gas, carbon dioxide gas, water vapor, H2O vapor, oxides of nitrogen, NOx, NOx, and oxides of sulfur, SOx, SOx. Charging EVs use AC power utility grid electricity harnessed by the burning of crude oil or natural gas, as in gas turbine AC generators or natural gas powered steam turbine AC generators at your utility company. Can't get something for nothing. The energy density and material strength of crude oil derived energy and materials are only second to nuclear power, i.e. plutonium-239 isotope. More about the nuclear electric battery in a later video. So the final conclusion, and this is as of 2024, electric vehicles are more efficient than gasoline cars. Electric vehicles are more expensive than gasoline cars. Electric vehicles are more expensive to maintain compared to gasoline cars, and electric vehicles are environmentally comparable to modern gasoline cars. So that ends this presentation analysis, electric vehicle energy density and cost analysis. Thank you for watching this video and have a great day.